This is third edition of Quantum Science Days, and first time we have an industrial demo. Thanks a lot for Classiq for sponsoring this event, supporting us, partnering with us, and also providing this demo. I think we already shared several messages about it. It will be the best if you have some student or academic email, then the platform comes for free, and then probably will give more information plus some free credits. So I think, yeah, Eden, thank you very much. I am giving stage to you. I will follow. Should we interrupt for questions, or we should wait at the end?
I have some slides of questions, and then I want people can open the microphone and ask any questions. And
okay.
Together with me, we have Tammuz from the CTO team. So any question Tammuz can answer either in the Slack channel or here in the chat of the Zoom. So
okay. Okay. So I am leaving stage to you. Thank you very much again to you and also Classiq.
Okay, perfect. Thank you, Abu, for the introduction and for the great organization. I'm Eden Schirman. My background is in physics and electrical engineering. I worked as an algorithm developer for a couple of years. I did my master's in quantum dynamics at Imperial College London, and now I'm the manager of Classiq for academia. So Classiq is the leader quantum computing software company. We raised over $60 million in funding, and we have roughly 60 people, world-class experts of quantum computing and classical algorithms as well. We are mainly based in Israel, but we have offices in the Netherlands, in the States, and soon in Japan as well. And until a couple of months ago, we were mainly focused with Fortune 500 companies, like the announcements with Rolls-Royce we had recently, but also with big pharmaceutical and bank companies around the world. And in recent times, we also started a new direction for the academic population, so for researchers and students, and I assume some of you in the crowd are from academia. So to enable academic people to use the Classiq platform for free for the rest of the year, and to fully utilize this for their education or for their research perspectives. So what we are going to discuss and do today, so we'll start by roughly 20 minutes introduction to Classiq and the platform itself. And then we'll start with hands-on and first end-to-end use of the Classiq platform. So Classiq is from generating your algorithms, your model, to analyzing them, debugging them, and then execute it on any real hardware. This is everything you are doing with Classiq. So you will do it in 30 minutes from now. And then you'll generate your own quantum algorithm that will have some exercises, and then you can run them on real hardware. So on IonQ machine, Rigetti machine, IBM, any available machine on the cloud. So what Classiq does, Classiq allows you to interactively design quantum algorithm on a functional level, to optimize them and to execute them. So this is high level of words. So let's try to understand what does it mean. So the first pillar of the Classiq is we can understand it through the following example. So now we have a quantum circuit. We can see roughly 6, 7 qubits. We can see some CNOT, some Toffolies, some rotations. Okay, we can maybe try to understand what's the functionality, what this circuit implements, what kind of algorithm. And here we have a different quantum circuit. So we have CNOT, QFT. Okay, we see it's a totally different circuit from the previous one. And here we have a third quantum circuit, which is, again, totally different, even maybe different number of qubits. We have only Toffolies and CNOTs, no QFT, no phase. Okay, so 3 totally different circuits. What's going on here? The main thing is that all of them, they implement the same functionality, the same algorithm. All of them implement a quantum adder that take 2 quantum registers of 2 qubits and coherently add them together. So now we can start to understand the heart of Classiq. So in Classiq, we design our algorithm and our models on a functional level. So we were used to believe, I think, in the community that the quantum algorithm is synonymous to a quantum circuit. While it's true from some building blocks, for general algorithms, it's definitely not true. So a quantum adder that takes 2 quantum registers and coherently add them together, it can have infinite amount of circuits implementation. So we can add more auxiliary qubits. We can change the circuit depth. We can change the implementation of different building blocks. And here we can see an example. So 3 different quantum circuits that all of them, they implement the same functionality. And this is the heart of Classiq. So with Classiq, you design your algorithm, your functional level, and then you let the Classiq platform to generate an optimal quantum circuits for you. So you don't need to design on the gate level. You don't need to design the specific quantum gates. You can do it if you want to, but you don't need to do it. You can set the functionality that you want and set some constraints and resources that you want. So for example, if you want to run the quantum hardware on a trapped ion machine that has all-to-all connectivity, the circuit implementation will be different than a superconducting qubit hardware, that you have a certain hardware connectivity map. So the gates will be different, the quantum circuit at the end will be different. And if you have more qubits you want to use, so maybe you can use more auxiliary qubits and then make your circuit and the depth of the circuits lower. So with Classiq, you design on the functional level, and then the Classiq platform optimize and generate the optimal quantum circuit for you. So this is the first pillar of Classiq. Okay, so once we are receiving a quantum circuit, let's say we receive this circuit, and now we want to view the circuit and understand what does it do. So here it's a quantum circuit. It starts here and then continues here and continues here. And we can see on the gate level. But okay, sometimes we do want to understand what's the gate level implementation. But on the other hand, it's quite hard to understand the functionality of this or to understand what building blocks are composed here. So what's going on if we take one step higher and then we bunch some gates together according to functional building blocks? And now we can see, okay, we have state preparations here, and we can see adder at the first part of the adder, the second part of the adder. Okay, and it gives us more clues about how the circuit is designed. And we take one step higher, and now we see, okay, the first part is actually an arithmetic oracle. Okay, so it helps us understand and analyze the circuit. And we can continue go up and up and up until we can understand that this is a Grover algorithm with state preparation, and Grover operator. And we can go up and down in the hierarchy level to understand either the functionalities or the circuit, the gate implementations. And sometimes we want this, and sometimes we want this. So this is the second pillar of Classiq platform. So we have a very, very nice visualization techniques that we can zoom in and zoom out into the circuit that we receive from Classiq platform. And it helps us further analyze and maybe sometimes debug and think about better implementations of our circuit. So here we can see an example how we zoom in, zoom out. We can collect and name some registers together. So for example, here we name the register A and B, and we can scroll around our quantum circuit. And we have here some navigation map. If we have very, very large circuit, so this is allegedly large circuit, but it's only like 7 qubits. If we have hundreds of qubits, we need some way to navigate and to understand what's going on. So we cannot just plot it in Python and see what's happening. So we need some way to interactively go and walk with our circuits. So this is a very, very good tool for this. And as we'll see later, you don't need to generate your circuit from Classiq. You can also import some circuits from Qiskit, for example, or Kazem or QSharp, and then just use the visualization techniques of Classiq. Okay, so this is the second pillar of Classiq. And let's discuss some execution. So at the end, we want to execute or to run our quantum algorithm and quantum circuits on real hardware or either on large simulators. So let's take an example. We have some unitary, our quantum adder from what we've discussed a few minutes ago, that coherently adds A and B together and results a coherent superposition of A and B. So this is the final quantum circuits that we receive. And here we want to add A and B. A is a superposition of 0 and 3, and B is a superposition of 1 and 2. And we expect to get the output that is equal superposition of 4 possible states. So here we can understand it as 0 plus 1 equals 1, 0 plus 2 equals 2, and so on and so forth. Okay, so I don't know how much, what's the percentage from you guys that actually run some algorithm on real hardware. And I assume from the workshops and from the people I encounter in academia, researchers and students, that even if people actually run on real hardware, 99% of them only ran on IBM's hardware, and no one ran on other hardwares because it's actually impossible to do it, because there is no easy way to actually get access to other platforms, although there are great hardware providers out there. So we ran it first on a simulator. So we ran 2048 shots, and we expect to receive, roughly speaking, an equal superposition of the 4 possible states. And then we ran it on IonQ Aria, which is one of the best quantum computers that is available out there. And we really didn't know what to do. And all the academics people that we are in touch with, they didn't know what to expect from the results, because people say all the time, okay, the hardware is not good enough, everything is noisy. Okay, so we can just take it for granted, or we can actually run on quantum computers and test what's going on. So we actually run it on Aria, and from all the possible shots that can go either to the true signal, so we have only 4 possible bit strings that we expect to receive, and we think that we'll get some noise. So here we can see bad results that are in the form of noise of the quantum circuit. So 0 + 1, 0, it represents a bit string, which is completely noise. So we were wondering how much from the shots, what's the percentage of shots that is concentrated only in the true signal. So I let you guys guess for yourself, because we cannot have online guesses now, but we're really surprised to understand that 100% of the shots were within the true signal, within the 4 possible results, 4 out of 64 results. So it does not mean that we don't have any noise. It just means that all the noise was altering the probabilities from uniform distribution on the left to a different distribution, but only 4 possible bit strings we received back. And this is quite remarkable. So the quantum circuit that we executed is 7 qubits with a depth of 37. And it really means that we can actually do some stuff, of course, not gaining any quantum advantage nowadays, but we can do some stuff, and we can try to push forward what's the possibilities of implementing some quantum algorithm. So now with the Classiq platform, you can actually run on any available quantum device that you have in the cloud with 3 simple clicks. So here you just choose your quantum circuit that you have, the vendor, provider, and the execution type, so hardware or a real hardware or simulator, and we can choose from a list. So here we can see IonQ QP Aria, configure the number of shots, press run, and that's it. Now the job is sent to the IonQ machines, and once the job will be back, because sometimes we have long queues, you can go back to the platform and receive the results over there. So specifically for academics people, if you registered with your academic domain, you get free credits to run on any available hardware via Azure. So you can run on the IonQ machine, both the Aria and the Harmony. So it's like 23 qubit and I think 11 qubits machines, or with the Quantinuum machines, or with the Rigetti machine. So we can use the credits to run on any available hardware, again, with only 3 simple clicks. And I think it really opens up new possibilities, a new frontier on easily running on real hardware. And then you can, if you're doing research on error mitigation, you can try to develop new mitigation techniques, and within small time scale, just receive your results back and analyze them. So this is the 3rd pillar of the Classiq platform. So now we can understand what does it mean that Classiq allows you to interactively design with the visualizer quantum algorithm on a functional level. So we design the functional level, not the circuit itself, to optimize them. So this is the Classiq platform do by itself, and then to execute them on any real hardware or a simulator. So for example, with NVIDIA, we just published a nice work that we, with NVIDIA and Rostos, we simulated a 39 qubit circuit with a depth of almost 1 million. So it was simulated on GPUs. So also you can access this kind of classical compute power also from Classiq. So if we take a look on the high-level scheme of the platform, so we first have the model. So it's a high-level functional model, and then we send the model into a Classiq synthesis engine, which is our backend online, and this generates an optimal or general quantum circuit according to the model that you want to design and according to available resources and constraints. So what's the hardware that you want to actually run on the end, and then we can optimize the circuit for a specific hardware, or what's the number of qubits you want to use, or what's the maximal depth that you want to use. So Classiq generates the circuits according to these constraints. And then you receive back the circuits, and then you can further analyze and visualize it with the visualizer. And everything is sent to the execution on any available hardware provider. So further cool stuff, you have really nice analysis techniques. So for example, if you have your algorithm and before you send it to execution, you can see how it is transpiled to the different hardwares. So you can, let's say you have the quantum adder, and then you want to transpile it or to send it for execution for the IBM machine, the Tokyo IBM machine. So you can transpile it with, or ask the Classiq platform to do some analysis and to understand what the depth will be on the IBM machine and what depth will be on the Continuum machine. So this is taking advantage of the all-to-all connectivity, and what's the multi-qubit gate count. And you have many, many nice analysis tools that you can use with the Classiq platform. You can see the qubit mapping. So what's the logical to physical qubit mapping and what's the hardware connectivity mapping. You can understand what the resources that are utilized. So what physical qubits and how many gates are used on each physical qubit. So there are many nice analysis techniques that you can actually use with the Classiq platform. So how you work with Classiq? There are two ways to interact and actually design your algorithm and execute your quantum circuits with Classiq. So first is a web-based IDE. So for you guys that already onboarded and tried to register and started to play with the platform, so you did it through this platform.classiq.io, and you can just log on platform.classiq.io and then start playing around. So the homepage is available to anyone, and on the left we can see the features of the Classiq. So we have the synthesis where you generate models. We can see the visualizer, the execution, and all the jaws back on the left, and these are available only for people that registers to the platform. So this is the first way to interact with the platform. And we have also a Python SDK. So we can download and to do pip install of the Classiq package and work with any favorite Python SDK with Jupyter Notebooks, VS Code, or whatever you want. And then in each stage of the Classiq end-to-end process, you can go back and forth between the Python and the IDE. So you can generate your model from Python and then export it and view the model itself on the IDE, on the web page. Or you can generate the model here and only and send for synthesis and then see the circuit here. So you can go back and forth and just whatever is more convenient for you. So again, everything is platform.classiq.io. This is the starting point, both for the SDK and the IDE. And from there, you can use the powerful tool of Classiq. So in the homepage, when you go over there, you can first find the basics. So you can find some basics tutorials like state preparation, arithmetic, Grover. And this is the best way to ramp up with Classiq and to master the tool. So you can just go with the order here. Then you have some advanced tutorials. So you have optimization and HHL and Monte Carlo that will take you through how to fully utilize these examples. We have the Slack community. Everything that you want to ask, you want to know, you need some help, something is not working, you need any support, you can ask everything in the Slack channel. And we have our support team that constantly monitor the Slack channel and will help you with whatever. And also if you want some new feature, so you thought of something cool and you want you want Classiq team to develop it for you, you can ask it over there. And if it's something that many people would want, probably we'll develop it because we want to create the most useful quantum software tool for you guys, for quantum developers. So feel free to really utilize this source of community. And we have the user guide. So relates to the previous talk that we had. So in the user guide, we can see some sample programs and, for example, the quantum support vector machine. So we have a pre-built quantum support vector machine application in Classiq, so you can go through this tutorial and many, many more tutorials over there. The first step is to do the onboarding. So some of you made and some of you can do now, and Tammuz and myself can help you do that. So you just go to onboarding and start with the registration. Again, now the platform is free only for academics. For the coming days, we open it to all participants of the Quantum Science Days. So even if you're academic or even if you're not academic, to start the onboarding, you can just press the academic registration, and this will take you through the entire flow, how to continue and how to install the Python SDK. And now I'll show you some, in less than 1.5 minutes, what is the end-to-end quantum software development. So from the home page, we can go to the synthesis on the left. And here we want to synthesize some state preparation. So we can see the probabilities we want to synthesize. We can see the maximum width that we want to allow. We can choose some optimization parameter and further metrics. And then we get the circuit. And then we can change the name of the circuit to the state preparation example. Here we can see some parameters, the circuit information. We can zoom in and zoom out into the circuit itself and further understand it. Or we can just collapse all in. Understand. Here we can see the width and the gate counts, both of C0s and unitaries. And I want to send for execution. So we don't want to wait for a couple of hours. So let's do an IonQ simulator. We choose 248 shots. We name the job. In terms of the process, the IonQ simulator and the QPU are exactly the same. It's being sent to the IonQ machines. Over there, it just chooses either to run on the QPU or in a CPU. The QPU, the queue over there is longer, but the process is the same. Everything is just the same. And here we receive the results back. All the results are here aggregated in the left. And we can see the results, and we can further change between the percentage and counts and truncate the data and export it as a JSON and further analyze and work on our results with Python, with the Classiq SDK, or with whatever you want. So this is in less than 1.5 minutes, an end-to-end quantum software development from generating your model to understanding the circuits to real hardware execution or a simulator, everything aggregated in one place, quite intuitive and really nice platform. Any questions so far? So Abu, if it's fine with you, people can open the microphone and open the...
Yeah, I think it would be better. There are already several. Let us not go through. Can maybe raise hands and I can just take all questions. And then one problem, several people using their academic email, but still getting this authentication problem.
Yeah, so there were some universities or some academic institutions that were not registered in our list. So we added them to the list. And now the people that had this problem, they just need to quit the Classiq platform and reopen it. And if the problem remains, so just to delete the cookies of the browser and then do the everything again, to sign in with their credential, not to sign up again, just to sign in again, and it should work.
Okay, but I already reporting some still, but probably it will not be ready for this time. But they can try maybe later, correct?
Yeah, correct. If they try to, some of them we already loaded to the platform, to the list, and if they can try again to quit and reopen and delete the cookies, that would be great. And if the problem persists, so just to write in the Slack channel and we'll help. We'll try to help now with Tammuz and myself, and if not, it will be later on tomorrow.
Okay. So we will share this recording probably after a few hours. So if you have problem now to test it, just share your domain. The best would be go to Slack, share directly. If not, if you share here in our Discord, we will still pass it. And then, yeah, you can complete. They are adding. So some other questions, just raise your hands and we can take one by one. I saw several questions. Okay, Emine, you can start.
Okay, thank you for the presentation. I have a question about the Oracle. When I use Qiskit or SIG, I define my Oracle with Python. So I see in this platform, the Oracle already defined. So how can I change this?
So you can either use a predefined Oracle, or you mean that you want to define your own quantum circuit that implements a specific Oracle?
Mm-hmm. So I can change Oracle. Mm-hmm.
Yeah. So you can you can design your own circuit basically also with Classiq. You can do a function-based circuits. So you can design your own function. Either you can start from a unitary or design it by just plugging one gate by one gate. as you do in Qiskit. So you can do both ways, either design the specific circuit with the specific oracle that you want, or use the Classiq platform to generate an oracle for you.
So can I use the Python also for the oracle?
Yeah, exactly. And you can advise the user guide, everything. You have the documentation over there, how to actually do it, and what's the syntax of generating the model, or generating the unitary or user-based function. So everything is just detailed over there.
Okay, thank you.
Welcome.
Okay, some other question, please raise your hand.
I see there are 33 questions or messages in the Slack, so in the chat. So maybe something from there, or
You can go. It would be easier if they ask directly.
Yeah.
I've
heard someone that wants to ask, maybe.
Okay.
No, I said that I answered most of the question on the Zoom channel.
Okay.
Tab was already answering. Okay.
Okay, great. Okay, so if there is no other question for now, we can continue, and then there will be further down the road another time for more questions. Okay, so now, guys, it's your turn. So what does it mean? What's the demo that we just did? So the 1.5 minute of going end to end with Classiq. Now it's your turn to do it. So what you want to do? So I want you guys to go to the synthesis page. So log into Classiq and generate a model of the default state preparation. So as we saw, we just go to the synthesis, and then on the right-hand side, you have the state preparation. We can press it, and then on the bottom right, we press the synthesis. And then the visualization will open, and we view the circuit, and we can change the circuit name to what's name you want. And then you go to the execution page and choose the vendor and choose the hardware. So you can choose either IonQ Simulator or IBM Air Simulator. If you're non-academic, so you don't have access to the Azure credentials, so you'll need to use the IBM Air Simulator. Both simulators are good. And then you need to configure the number of shots, whatever you want, choose the circuit name and press run. And then you automatically go to the jobs page, and you can see the jobs over there. So if I go for the Classiq platform, so I'm going here to the synthesis. I press the state preparation. I will press synthesis, and then it will direct me there to the circuit. I receive this kind of circuit. I can play around with the visualization, and I can understand the circuit depth. I can change the name by double-clicking here and changing the name. I can also change the name of specific building blocks. So I can change the name of the building blocks themselves, either the state preparation or some of the gates, if it helps me. And then I can go to the execution. Here I need to choose the circuit. So the circuit name that you gave it. Here you can choose the vendor, so IBM or Azure. Here you can choose the execution type. So for now, we're doing simulator. We can choose what we want. So we can choose the Air Simulator, configure the number of shots, choose the job name, and then we press run. And then we will go directly to jobs. And in the jobs, the proper job will wait. Yeah, I see a question by...
Yeah, I think David has a question.
Can you show steps? Because not everyone can access that. Can you just show step by step to show us? We can see it. So that's easier. Because otherwise, people cannot do anything now.
Okay.
Can you just show steps? Yeah, just do easy one for us from beginning to end. That'd be easier for us.
Yeah, no worries. So Abu, can you please let me reshare the screen? I cannot share my screen. I have the host disabled participant screen sharing. So Abu, if you can please enable me. Okay, thank you. Okay, so from the home page, I'm pressing synthesis. I'm going to the synthesis, and here I can see some pre-built functions. So we have VQE, varieties, Grover. So please press the state preparation. And here we can see this is the Q modes. This is the model, the functional model that Classiq generates. So later on, we'll change the probabilities. But what we can see here is the probabilities of the state preparation that we want to have. So this is sort of a pyramid state preparation. And here we can see the error metric that we will have. So we'll use a KL divergence with some upper bound. And here the maximum width, maximum depth. So we go over here. After you press state preparation, you press synthesis. And now we receive the circuit. So after we receive the circuit, we can do double click and change the circuit name. So live demo. We can confirm, and we can also change here to state preparation. Here we can see the information about the circuit, and then the 1 qubit gate and 2 qubit gate count. And now we can go to execution. We make sure that we have the live demo circuit chosen. We go to, let's do the Azure one. And we can choose IonQ simulator. We can choose 248 shots and live demo job and press run. And then it will direct us to the jobs page. And now it's going to IonQ's backend. So it will take a couple of seconds, although it's on the simulator. And now we can see the results. So here we can see that we received the pyramid, but it's not the perfect pyramid. So it's not because it's a noisy simulator. It's because we have a trade-off between the depth of the circuit and the accuracy that we'll receive. So if the depth of the circuit was not limited by 1000 as we wanted it to be, so we receive more, the pyramid will be sharper, and it will be resemble more to the perfect and ideal situation. But it's a trade-off between the depth of the circuit that we want and the results of the state preparation. So please let us know if you have managed to do it. You can share it in the Zoom chat, or raise your hand in the Zoom, or just give us some signal that you actually managed to do it. Yeah, I can see one, Luis hand. Okay, Luis, Victor, perfect. More hands, more hands. Okay, let's wait until we have at least 10 people that signal us that they actually made it. So we have 2, Luis and Victor. So if anyone else has a problem, so please write it, and then we can try to help. Okay, we can see 3 people, 4. Very nice, very nice. So let's wait maybe 30 seconds more. We can take some questions. The execution failed. Okay, so meanwhile that people are still trying to complete the end-to-end experience. So now we'll show you a cool feature. So the cool feature break. And there are many, many features of Classiq platform. So it will take time to really fully utilize its capabilities. And so we'll try to give you some glimpses. So here we can see with the visualizer that we can actually change the circuit. So we've done it. And we can, again, zoom in and zoom out. And now we see that we have a quantum register, but we don't see it in the circuit as register. So we want to combine the 2 qubits, or the representation of them, into 1 qubit and name it. So this is the register that represents A. And here we have the registers that represents B. So when we come to analyze the circuit, it will be easier if we can bunch everything together according to some logical meaning. So the 3 qubits down there, it's A plus B. It's the output, basically. So we can either just name all of them or to combine them together. So this is one example of further feature that we have with Classiq. Okay, so I see more hands in there. That's great. Okay, perfect. So I think we have at least 10 people that made it, I hope, and it seems on the way. Okay, so let's continue. So now we have, it's your first IDE-based quantum algorithm. So what does it mean? Now I want you not to use the default example that we had, but to go back to the state preparation, again, to the synthesis, to the model, what we had before, and generate two quantum algorithms with the following probability distribution. So now we want a probability distribution over eight possible states. So we have 3 qubits in the quantum register that we want to have the state preparation upon. So it's 0.5, 0.15, 0.3, and a symmetric continuation of that. So 8 states, we should receive some symmetric pyramid, basically. And we want to do 2 quantum algorithms. So we want to generate with a different error metric. So before we chose the KL divergence metric, and now we want to choose the loss of fidelity, which is basically just the fidelity. And this is a common metric that we use in quantum information science. So this is the syntax that we'll use, the loss of fidelity. And we want to choose 2 upper bounds, one to be 0.01 and one to be 0.1. So one of them, we want it to be more accurate, the 0.01. So this is the maximal error that will give the algorithm or the quantum circuits that you want to implement, and one will be less accurate. And of course, there is some trade-off between the accuracy and the depth of the circuit. And here it will be the first example that you actually generate the model, and you let the Classiq platform to generate or to optimize this trade-off for you. So you can choose to optimize over the depth. So there's optimization parameter, and we'll go over it in a second, over the depth. And we want to synthesize both circuits. And after you synthesize the circuits, we want to compare the resources. So understand what's the depth and the number of gates for each quantum algorithm, for each quantum circuit. And we'll see what's the resources and compare the resources. And then we can execute it and understand what are the trade-offs between the resources and the accuracy that we can see with our eyes. For academic people, you can also run it on the IonQ Ariel QPU, which is basically one of the, I think, top 3 quantum processors that we have in terms of accuracy or quantum volume or algorithmic qubit out there. So it's really nice that we have the access to the ability to access it. So you can run it with the 1024 shots and receive the results when they are back and see how is it going. And in addition to that, I want everyone to run on a simulator, either IonQ or the Air simulator, and they compare the accuracy. So before I'll go and show live how it should be. So this is what we expect to receive. So 2 quantum algorithms, at the end, 2 probability distributions, one for the less accurate model, less accurate algorithm with 0.1 error bound of fidelity, and one for the more accurate one, and to compare the resources for the 2. So this is the final results that we want to have. And now let's take 5 to 10 minutes and to try to do it. And we are here to help you with questions. And first I'll go here and try to give you some more directions how to do it. So we go back to the synthesis, we go to the state preparation, and here we can see the probabilities. So we need to delete all other probabilities, and we need to choose the probabilities that we want to have. So it's 0.05, 0.15, 0.3, etc., etc. Here we change the KL to loss of fidelity, and we need to change here one time for 0.1 and then the other time for 0.01, and we want to choose optimization parameter over the depth. So we go here, choose the depth, and here it's a nice API that automatically change the code that we have here. And after we complete the probabilities, so we need to have 8 probabilities over 3 qubit states, and then we press synthesize. So we do one time for the upper bound of 0.01, we receive a circuit, and then we'll go back to the synthesis and do with the other upper bound and do another synthesis. Once we finish both of them, we want to do the execution and compare the results. So we are here, Tammuz and myself, for any help. If you have any question so far, this is one of the circuits that we will receive. You can see it here. And let's take a few minutes to try to do it. And please raise hands and send also in the general Slack channel of Classiq a screenshot if you finish. So if you finish with one of the algorithm, you can just in the general send a screenshot and say finish, and then we'll get some notion of you guys how you are progressing. So we'll take 5 minutes, and meanwhile,
Can you put in the screen the instructions, please?
Yeah.
Thank you.
So feel free to open the microphone and camera, and if you have questions, we are here meanwhile to help you with anything. So we'll take 2-3 more minutes to complete this exercise, and after this we'll go to the next exercise, or to the next way to work with Classiq, so with the Python SDK. So if anyone has finished this kind of exercise, we can you can start going from the home page to the onboarding, or to the basics, and start to get the feeling of how to work with the Python SDK. So Omar and Maja, you say that you're still waiting in the queue. For the real hardware, it might take time, because I think all of the vendors, they have some queue times, and you can see also in the execution what's the queue time. But you can just continue work with the platform as you wish. So you can send more execution to the same hardware, to simulators, to anything else. You can close the platform, go back. You don't need to stay there. So the job is sent, and it will be saved back to your personal area and back to the jobs page when you are back. So you can send basically multiple execution in parallel, and then whenever something is getting back, you can just analyze the results. So although the job is in the queue, you don't have to wait in the queue as well. And this is very nice advantage. It's not like with only a Python that you need to keep it open and the script is stuck until you get results back. You can just send it and come back whenever you want.
Edan, how much credits do they have?
That's a good question. So for now, you can use the credits. For now, it's unlimited until the point it will be limited.
Currently unlimited, so they can enjoy.
Yeah, for now, it's unlimited until the point that it will be limited.
Okay.
But personally, I have still my also university account, and it's really interesting to explore the hardware. Last year, I did my master thesis in quantum algorithm, and my supervisor told me, yeah, it's a waste of time to run on real hardware, and we don't have access, and it's a hassle. And I was quite disappointed. But now with this tool, it's really nice because you get access to anything. You can just explore it and see the results and analyze the results. And actually, today's hardware is not that bad. Again, we don't have anything close to quantum advantage. But in order to push forward to gaining the quantum advantage, whether it be in 2 years, 5 years, 1 year, 10 years, I think nobody knows. We need to know what's the state of the art and to have access to the state of the art. And as we, as a community, have more free access and available access to the state of the art of what's available out there, of the quantum processors and the best error mitigation techniques and the best software tools and the best algorithmic capabilities, we'll further know what's the possibilities. And then we'll develop better algorithm and better hardware. And at the end, we'll reach the point that we do have the quantum advantage.
But practically now they can use Classiq and access these hardwares unlimitedly.
Yeah, definitely. So,
and it will not be closed tomorrow, so they can even do some research maybe.
Yeah, definitely. So this is the point. So we are having a close collaboration. Yeah, with both courses. So we have one in the Technion and one in Singapore, and we had one course in MIT that people actually went to the hardware and they're exploring the hardware. And we also have researchers that working with the platform and trying to fully exploit its capabilities. So here we can see with the jobs, I have all the jobs here. So jobs from May 16 and previously, and here I have one job for Quantinuum that I sent today. And usually Quantinuum machines are not available for immediate access, so they have long queue. So I sent it today afternoon at 4 p.m. and I'm still waiting. But it doesn't mean that I cannot send. So this, I send the live demo. It's the simulator. We ran it like 20 minutes ago, but it's in parallel. Nothing is
okay. Because I thought this credit is limited, like monthly or daily or something like this. So it's unlimited. It's great.
Yeah, of course, at the end, if there will be massive usage, so someone will limit it. But for now, people can enjoy the free access of the credits. And also the hardware providers, so both AWS and Azure, they give free access to personal use, I think for academics, and I think maybe also for anyone. And what you can do also once if the credits are done, and this you can do also if you are not academic. So to go to execution, let's say with AWS, not with Azure, so with Amazon bracket, and then we want to choose one of the hardware. So let's say the Harmony. So it's the IonQ Harmony machine with 11 qubits. The number of shots, we can configure the job name. And once we press run, we need to log in our credentials. So you can go to AWS to Amazon bracket and then open up the credential. You need 3 credentials, the S3 bucket name, and you can get the credentials over there. And once you open an account over there, you get free access. And I think going back to the platform, it's really intuitive and really nice to send everything here and everything is aggregated. You just put in the credentials, connect it and run, and then it's working. So you can also use your own credentials also with IBM. So for example, if you want with IBM on some real hardware, you can choose, you can press run, and then you need to bring your own access token and hub and group. But anyone can open an IBM account also for free and get the free access token and just put everything here, connect and run, and that's it. So it's a one-stop shop for everything, any hardware provider, any vendor. And in that sense, it's nice that it's aggregating all of them together.
Very good. David, you have a question or you finished?
I have a question here. I can run with the simulator where IonQ simulator, but I run with the IonQ area, and it runs quickly. It's a failed with unspecified error. So how do I do with that?
Okay, so if it's
nothing, just the error there, what should I do?
okay, so if it's failed with an error, it's failed with an error. So you can.
I don't see anything unspecified, so I don't see what's going on. So it didn't say anything what error. It just undefined error.
Yeah. So most of the errors are coming back from the vendors themselves, from, let's say, from Azure or from IonQ. And so if you can raise the question with the error in the Slack, so we'll try to understand this. And probably some of the times they downgrade the machines for calibrations and further control. So there are several things that can go wrong in terms of why it's not working. But you can raise the question in the Slack and we can try to help. Most of the time it's because something of the hardware providers or the vendor machines.
Also, I just realized, I know you guys have an announcement with the Microsoft Azure Quantum, right? You have funding. Is that if the funding with the Microsoft Azure Quantum running out, then we won't have any access, right? Is that because of funding from Microsoft, right? If they're running like so much money, right? We use so much, by the time this funding is over, we have limited access, I suppose.
Okay, so I'm not sure I fully understand the question. So let me treat some of the points and then you'll send if you have further questions. So
yeah.
The academic program we initiated with Microsoft in a collaboration, and
yes.
part of the partnership is that academic people do receive free credits to Azure for their machines. And as we continue, we'll see how the partnership with Microsoft continues with the credits and further work that we are doing together. On the other hand, you still, although you have free credits with Azure, you still have access to all hardware providers, IBM, Amazon, IonQ, NVIDIA, everything that you want to execute online, you can access. You can bring your own credentials, or if you have some other credentials, you can use them. So I'm not sure it's fully answering your question. I hope it does. Okay, so let's quickly come back to the results here. So I hope some of you have received the results. So again, one of the algorithms that we wanted to generate was with error fidelity of 0.1. We can see the circuit depth is only 9. So it's quite small with 3 qubits. It uses only 4 CNOT, so 4 2-qubit gates and 8 single qubit gates. But we see that we wanted to receive some sort of a pyramid, and it's not what we received. Again, it's not because it's a noisy simulator, it's because of the accuracy of the algorithm that we wanted to generate. So here we can see the trade-off between the depth and the accuracy. On the other hand, here it's a more accurate model that we wanted to generate. It resembles more to the ideal pyramid that we wanted to have, or the symmetric pyramid. But here the circuit depth is way larger. It's 96, and we have 52 CNOT. So this is the trade-off between the algorithmic accuracy to the resources that we have. And eventually, with the near-term devices, this trade-off of the resources will map to a trade-off between the algorithmic accuracy and the hardware accuracy. So we'll know that the hardware has some limitation, and if we cross some circuit depth and use more 2-qubit gates or more CNOTs, that it's a maximal available in terms of the fidelities, in terms of how the hardware performed. So we'll get this trade-off between the algorithmic accuracy and the hardware or the noise accuracy. And I think in the near term, the ideal way is to try to optimize this trade-off between what's the maximal depth that we can get meaningful results out of. So we'll try to do some more algorithmic accuracy with to push it forward, and then we'll see if the depth is too much for today's hardware. And now we can play around with this kind of tools that we have. Any questions so far? Yeah, I can see one question.
I think Emine had a question.
Yes, I finished, but I have a question here. how can I export my graph, for example, like JPEG or PNG? So it's only export like JSON. I don't want this.
That's a perfect. So here you can press and
okay.
export as JPEG. So that's a
Okay.
perfect question. You can see the JPEG, and we can export as HTML as well, which is also nice because you can send an interactive circuit to anyone. So let's say you are an instructor in a quantum course. So you can generate in advance this quantum circuit and send it to the students. And then they can use it, or your collaborators. And then they can interactively use it without using the platform. So you just need to send the HTML itself. So that's a great question, and thank you for asking.
Thank you.
Sorry, can you show the both diagram in the same page? I only show one by one. How do you do that? Like both jobs show the output side by side.
So you want to see both jobs in the same page?
Yes.
Okay, so that's also a great question. This is a feature that we actually nowadays working on. What I've showed you, it's from my slides. So I just print.
I'm sorry. I saw you can.
But this is a great feature that we are working nowadays. And again, for you guys, as more as you'll say what you want for actually developing quantum algorithm and quantum software, write in the Slack, contact us. Mainly in the Slack, it's the best way, and ask for more features. So if more people will say, we really need this comparison between two probability distribution, and I don't know, 50 people will say, it's something that will develop quicker and quicker because there are infinite amount of features that we want to develop and finite amount of resources that we have here. So as much as things that you want to push forward, it will help you to actually develop the most suitable tool for you guys. Okay, and now let's do another feature break. So let's say you have your own quantum circuit in Qiskit. So you run something on Qiskit. Here, for example, you have the QFT. And as we know in Qiskit, it's great for many things, but the plots, you only have one plot and you can do decompose and decompose and decompose, and you have in JPEG. Let's say you want to import this into Classiq. So how we can do it? So we can do, we generate the QASM code from the circuit. So we just do the circuit and QASM and get the file name. And after we save the file name, we can actually import it in the Classiq platform. So here we have the file name, and then we can download it. And after we download, we can just move back to the Classiq platform, to the visualizer. We press the plus button to open a new window, and we just drag and drop the circuit that we received. And once we receive that, we can visualize and understand our circuit in Classiq. And now we can also send it for execution for any available hardware. So if you're working, let's say for now with Qiskit, and you are running on IBM machines or IBM simulators, and you want to run on IonQ or Rigetti, or to compare different hardware providers. So I think this will be a nice way for you to actually generate your own circuit the way you did as before, but now you have a new way to access visualization technique and execution, and to access all available hardware out there. So this was the second cool feature break. Okay, so the Classiq Python SDK. Okay, I think in terms of timing, we won't have time to actually go through the entire process. So I just go through the instructions and how you can see everything and how is it working. So basically on the onboarding, if you press the academic registration after you are signed in, you'll have step-by-step how to install the Python SDK. So you just, as usual, pip install Minusio Classiq, and then you have the installation. There is many dependencies that the Classiq package installs along with the Classiq itself. For example, Payomo and many other dependencies. And then you need to verify your account. So you will see it over there. And once it's verified and you finish everything, you can have your Python environment ready, and you can work both Python and the IDE, the web page IDE. So let's go here. If you go to the home page, the onboarding. So I'm already registered. I can press the academic registration, and then I can go through the step-by-step. So I can copy and paste the pip install, and then I have import Classiq. So I open some Python script. I can do it from the shell, from the command line, or from the Jupyter notebook, and I need to authenticate. And now once I'm authenticated, so the Python SDK is linked to the IDE, so I can continue. And here there's some hello world examples. So this is the Python SDK hello world that we have. So a different probability distribution. We have the state preparation. We get the model. We ask the Classiq platform to generate a circuit for the specific model. And then with the circuit.show, it links us to the visualizer, and then a new website will open, a new web browser of the Classiq platform, and you can view the circuit over there. And this is the results that you will receive. So if anyone has done it and he has any questions, so you can ask now. Otherwise, after you've done the onboarding, you can go to the basics. And here we have a few tutorials that are going through how to build your own models from the Python SDK. So I'll quickly go only over the first one, and then you can continue to the hardest, not the hardest. It's going up in the level of difficulty. So after the arithmetics, and then the Grover search that you can build by your own. So let's say we define some probability distribution that we want to have. You can define this one, or what we defined earlier in the exercise. This is the final circuit that we've received at the end of the process. And now we'll go how you build this and how you generate some quantum circuits from the Python. So you have 3 steps in generating any model from Python. So the first step is define the functional building blocks. So functional building blocks are the state preparation, are the arithmetic oracle, are the Grover search. So these are the functional building blocks. And then we define the high-level model. So it's just a Python object of the model that we have. And then we wire the functional building blocks into the model. So for the state preparation, it's a simple example because we have only one functional building block. So the state preparation building block, and then we initiate one instance of the state preparation, and we give it the probabilities that we have. We give it the error metric that we have with the upper bound. And once we have this instance, this is the first step. And then we have the model. So we initiate another instance of the model. So this is a Python object that captures our algorithm or our algorithmic model. And then the third step is to wire them together. So we do model.state preparation. We want to wire the state preparation into the model with the state preparation instance that we initiated. And that's it. Now we have the model. So the model is hardware agnostic. It's agnostic to everything, basically. So we have the model. Now we can generate circuits according to specific constraints and according to specific resources. And the model doesn't change. So the model, it's the algorithm. It's the functionality of the algorithm that we have. And then we can take the model and synthesize a specific circuit. So take it from the abstract model to the specific implementation. And once we'll do circuit.show, a new open will open here in the visualizer, and it will have the circuit itself. Yeah, so here we have further details how to do execution from Python and further to walk through further examples, and how we can go from the Python SDK to the Classiq IDE back and forth and so on. So I really encourage you to go through it. And once you are finished with these 3 tutorials, I think you are ready to work with both the IDE and the SDK and really start to work for your own research or courses or for self-exploration. So I think this is a really nice ramp up. Any questions on that? Okay, so I think we are getting to the end of the tutorial, so I can share with the slides later on. So here we have some exercise, and I think it would be nice for the people that want to go through the Python SDK to actually do also the exercise, and it will help you improve and get along the Classiq platform. So I can send later on either via the Slack or via some other platform the exercise itself. And yeah, last but not least, so you can join our Slack channel. There's a large community over there, both to get support, feature requests, and any further question, any ideas, if you want to get help, if you want to organize some workshop for your community, your local community, anything, feel free to say over there. We have several channels, so a general channel and a support and quantum algorithms and executions, or just welcome and intros, and you can introduce yourself. Thank you.
Yeah, thank you, Eden. It was great. I think participants also fascinated about it. So as I told, after a few hours, I will put this recording also. You can still do this. This homework idea is very good. They can also test themselves with the homeworks. And probably joining Slack would be the best to get direct help also. Should we ask a few questions of Eden? Maybe you have time?
Yeah, definitely.
Are there some questions? We still have 6 minutes, let's say. I think Tammuz did a great work already.
Yeah, Tammuz, thank you for answering, I think, like more than 50 questions along the way. Amazing capabilities.
I didn't notice it at the beginning, but I noticed later he really answered everything. He was also in the Slack trying to answer that as well.
Yeah, right. You're welcome.
Yeah, thanks. I think, yeah, everybody satisfied. Only this authentication problem should be solved, and it already been solved, the ones who reported. So basically, you should go to Slack and report it. Okay, my domain, it's an institutional domain, please edit, and they are adding, and we are starting using. Yeah, thanks to Classiq for supporting Quantum Science Days. Also, thanks for this very nice presentation. Also sharing this great platform. Yeah, it's really fascinating. Thank you very much.
Yeah, thank you, Abu, for the great organization. And I really hope that it will be for the community to just use the platform and develop new quantum algorithms. We need the improvement of the quantum software as an ecosystem and as a community. So feel free to use this platform and any other platforms, but especially this platform for pushing forward the community.